So hello guys, today let's see micro resonators. Okay, what is a resonator? Actually, a resonator is a device that exhibits resonant behavior, oscillates at a greater amplitudes at resonating frequency than other frequencies. So basically what happens at this point, at this resonating frequency, the impedance of both, I will show you that. So now we are talking about series resonance, right? So basically series RL circuit will take. So one is a resistor, impedance and capacitor, where each will have their own impedance or reactance. We call it as reactance. So inductive reactance and capacitive reactance. So for reactance of resistor is same as R, but inductive reactance is XL and the capacitor reactance is XC. Basically those are also resistance only. Basically units will be ohms only. So XL in series it is omega L and XC is 1 by omega C. So basically when XL is greater than XC, the circuit will be like inductive because inductor is dominating the capacitor. When the capacitor is XC is greater than XL, then it is a capacitive circuit as the capacitor is dominating inductor. So since there is basically we'll see a difference between both XC and XL. Okay, that is called total reactance, that is XT. Okay, so where XT is the XL minus XC or XC minus XL, anything you will take. So what you have to take is, in the first case, if XL is greater than XC, then you will take XL minus XC. If XC is greater than XL, then we will take XC minus XL. Okay, that is XT. That is called total circuit resonance. The total circuit impedance, that is Z. So that Z is the equivalent resistance. It is like an equivalent resistance. Z is equal to root over R square plus XT square. What is XT? We will see from the above. So that is what. So this is the equation for Z. Okay. So when you substitute what we want, when you plot a graph between the impedance and the frequency, we will get a graph like a parabola. So as this equation Z depends on frequency, because XT in the sense it is like omega L, right? XL is omega L minus 1 by omega C. That means it is depending on frequency, this Z. So that's why you are getting a varying with respect to the impedance is varying with respect to frequency. So at one point what happens, at this point both XC and XL will be equal. So at particular frequency the both XC and XL will be equal. That frequency is called resonance frequency. Yeah, as this circuit is in series, that's why it is called series resonance. Okay, like the same way for parallel also. So that's what. So microwave resonators are same as lumped elements resonators. So lumped elements are like resistor, capacitor and inductor comes under lumped elements. So microwave resonators are used in basically which obeys Ohm's law and all. Okay, so microwave resonators are used in filters, oscillators and frequency meters, tuned amplifiers. Okay, so this is the series resonant circuit where you can see the resistor, inductor and capacitor in series. So here they have plotted the graph between frequency, it is angular frequency, anything W omega basically. So omega frequency divided by omega naught. Basically what happened, actually this is the graph where at this point is FR, right? So basically what they have plot F by FR, that means every point in the graph will be divided by FR. At this point FR by FR, that is 1. So that's why at this point we got 1. Okay, that's it. No, so basically this, and it is plotted against impedance. So the Z. So okay, that's what the point where we have the minimum impedance is called as resonating frequency of the circuit. At that resonating frequency, the value of impedance is R. R in the sense resistance, only the resistance, because at that point what we have found, both RL and RC will be, I told you, no, RL and RC will be equal. That means there will be difference is 0 when it's XT is 0. So when you substitute XT is 0, Z is equal to R. That's what we got. So, and also to find what is the frequency value at that point, we know that XC is equals to XL. 2 pi FL is, by substituting the formulas as we got, that is omega L is equal to 1 by omega C, where omega is at 2 pi F, right? So substituting omega in terms of 2 pi F, all will be what happens. So that frequency what you got is root over 1 by 4 pi square LC. Okay, so 4 pi square we can take it outside, that means 1 by 2 pi root LC. So it is in terms of frequency. When it comes in the angular frequency, what we'll get, this 2 pi will be taken out that side. 2 pi fr is equals to 1 by root LC. That means 2 pi fr is omega, right? So omega is equals to 1 by root LC. So resonating frequency for a series series resonator, series RLC series resonant circuit is 1 by root LC. So that's it. So input impedance is also given us. So actually what happens, we have calculated the effective resistance, right? This is the actually, it is like only the what we can say, it is the magnitudes, basically these are the magnitudes, but when you try to write in the polar form, what happens, or rectangular form, so what happens, generally we will find in terms of radians, right? Sorry, this is a resistance, this is a resistance, and this is a resistance. But basically the resistance of this resistor plus resistance of inductor plus resistance of capacitor. So it's the same way, resistance of resistor is R, resistance of inductor is j omega L, and the resistance of capacitor is 1 by j omega C. Basically you should call it as impedance. Okay, impedance of resistor, impedance of inductor, and impedance of capacitor. So directly summing up, you got Zin. The input capacity, the input impedance is very low, maximum power will be transmitted to circuit. When the impedance Zin is low, then we can able to transmit maximum power. Now coming to the parallel resonance. So parallel means what? 1 by x, we know, right? 1 by y is some parallel resistance 1 by r parallel is equals to 1 by r1 plus 1 by r2. So the same way, so if you want to write that 1 by r parallel means in the reverse, r parallel is equals to the entire thing 1 by, right? So basically like this, 1 by r parallel or is equal to 1 by r1 plus 1 by r2, where r parallel can be written as what? This whole set 1 by r1 plus 1 by r2 inverse, right? 1 by of this, that's why we wrote like this. So that's what he wrote here also. So each term this is it has an impedance of what actually, what is the impedance of C? 1 by j omega C. L is 1 by L is j omega L, and R is the resistance. So that's why R1, R2, R2, if you consider 1 by R1, that is 1 by R, plus 1 by R2, that is j omega L. R2 is j omega, that's why 1 by j omega L, and C is 1 by j omega C, that is R3 is 1 by j omega C, 1 by it got again on the top, that is j omega C. So the same way, if you plot the graph, it will be looking like upward parabola, sorry, downward parabola. And since we have basically it will be looking like this, but when you actually divide it with resonating frequency, that actually this scale down basically. So 0 to here, this is the point where we got resonating frequency, that way omega naught by omega naught, that become 1. So yeah, so in this definition we can say at what frequency we will get the highest resistance, that if in a parallel resonating circuit, at what frequency we will get the highest resistance or highest impedance, output impedance, that point is called particular frequency is called resonating frequency. The point where we have same, the formula remains the same, 1 by root LC. Okay, so the formula is the same thing, 1 by root LC only. So resistance R has own significance, that is we cannot neglect with respect to other parameters such as quality factor. Okay, so one thing actually, so basically what we can conclude here, at resonating frequency will get a value of R, that means only the circuit will works with the resistor only. At that resonating frequency we can remove that inductor and capacitor, we can directly connect to be, and like basically it's like an it's like that. Okay, so basically it is only depending on the, at resonating frequency it is only depending on the resistance of the resistor. Okay, that's it. Here also in parallel also, both at resonating point, what happens, the XC is equals to XL, that's why it becomes 0 and only left with R. Okay, and at bandwidth for a particular band, at the given band, for a given bandwidth at that 1 minute, here is the value of impedance from R, where 3 dB is more than the point is called as 3 dB bandwidth of the circuit. So basically from R, we'll see the bandwidth where we'll see the value of R where it is 3 dB more. Okay, here that point is called 3 dB bandwidth of the circuit. Here in this circuit, this is here. Okay, 3 dB less. Okay, in this circuit 3 dB more, in this circuit 3 dB less. That is called 3 dB less from the highest peak. That is the bandwidth, 3 dB bandwidth of the circuit. That at that point, what is the value of R? 0.707 times of R resistance. So here also 0.707. Here the R by 0.707 in series at 3 dB. At 3 dB bandwidth, there is a value of a resistor will, or the value of impedance. Okay, the value of output impedance will be R by 0.707 for series resonating circuit. For parallel resonating circuit, the value of impedance, output impedance is at 3 dB bandwidth is 0.707 times R. Okay, so that's it. This is the end of this RF series. So thank you. Hope you like, share and subscribe.